Ladies and gents, welcome back to another Engineers podcast. Today I'm joined by two awesome chaps, Jake and Alvaro at PhysicsX. This has been in the making for a couple of months. PhysicsX are doing some awesome stuff, building AI to accelerate innovation. So we've got the improvement of design, manufacturing, operation of complex products and machines. We've got some really nice topics that we're going to be talking about today, centered around compute challenges, technology simulators, training data sets. So I'm looking forward to getting into this one. We've also had Jake come back from AWS reInvent as well. So he's a bit of a seasoned pro these days. Bit of background on PhysicsX, founded in 2019, $32 million series round last year, November 2023. So business is in a great spot, and we're going to be talking about some of the great stuff that they're building for our industries. I'm going to pass to Jake, who's going to give us an overview of PhysicsX. But first and foremost, thanks for coming to join us both.
It's a pleasure.
Jake, do you want to take it away and give us a snapshot into your background and then intro PhysicsX and double down on some of what I've said already?
Yeah, of course. So my background is largely around software engineering. About 10 years ago, when I started my career, I spent the best part of the past decade working in government across both software and cloud engineering. And that was through UK government, so working with citizens to deliver government services, as we typically do in the UK. And GovUK was one of the first governments across the world to really change their digital delivery of services. And with that comes a great ability to transform digital within government and technology within government. So I was part of the core of that across quite a few government departments in my time. And then more recently, in February 2024, joined PhysicsX on their mission to help advanced industries with something that is very transformative as well, in a slightly different way. So PhysicsX really works at the intersection of computer-aided engineering simulation, AI and machine learning across generative design and control loops as well. And really the ethos the company has is to reduce the iteration time on a design of a physical product from hours and days to seconds by moving across from sort of conventional simulation into inference as well. Conventional CAE has a long computational time and can restrict design exploration as well, because you're dependent on what someone can imagine or what someone can think of and the knowledge they have. And as part of that, we've been building large geometry models over the past few months that Alvaro will talk about shortly, and large physics models too. And the great thing about them is they learn to replicate the behavior of physical processes, so they're informed by physics. They have shorter runtimes, they need substantially less compute per iteration. We know that GPU availability over the past few years has decreased and got harder and harder. PhysicsX is about 100 strong people now. When I joined, there was only 50 or so of us, and we're really across multidisciplinary teams, across software, data science, machine learning, simulation, and AI research too.
Love that. I saw you join the business and I thought, oh, I haven't seen PhysicsX before, and went to explore further. And I know we put a pin in this to come back to it in 2024. So I'm buzzing to finally be here. Like, I've been snooping around on the website and seeing some of the innovation in some of the spaces that you're in, which we're going to talk about. So I'm lucky, looking forward to it. Alvaro, thanks for coming to join us as well. We've got a couple of subjects that we're going to go into in a bit, but do you want to give us a bit of background on you before we go back to Jake and talk about some cloud compute challenges and the geometry model?
Absolutely, yeah, sure. First of all, thank you very much for having me. It's a
Pleasure.
pleasure. I think so. Just a little bit of a background on me. I think my background is actually quite representative of the type of work that we do at PhysicsX, because I joined PhysicsX back in March this year, so a few weeks after Jake, as a machine learning engineer. I've been working in the past as a machine learning engineer for many years, but prior to that, I actually went to university to become an aerospace engineer. So I studied aerospace engineering. I worked as an aerospace engineer for a couple of years, designing airplanes with traditional tools. Um, and then I became a machine learning engineer, and then I found out about PhysicsX, whose mission was to transform engineering by using AI, and that sounded like something I wanted to do. And now here I am doing what I used to do, which is design airplanes, but now with AI and powered by AI. And I think the type of profile that I have is quite representative of what a lot of people at PhysicsX do. I think we have a big group of people very specialized, like Jake, who's like an absolute expert on cloud computing and on software. Um, although they're laughing, it's true. And then we also have machine learning engineers that understand the traditional engineering processes and the complexities of those engineering processes. And I think that combination is something that is quite valuable, and it's one of the things that has helped the tool that I'm going to talk about after, which is called Airplane. It's based on that understanding of both worlds.
That's the thing that excited me. There's a lot of traditional ways of still following the same software engineering, machine learning engineering approaches. But it's like you said, Jake, it's at that intersection of innovation in the automotive space is a really good example. It's about changing some of those industries, or how we actually use AI to change some of the design of those industries. So, like I said, buzzing. Jake, talk to us about some of the cloud compute challenges that you're facing. I think it would also be really good to set the scene on the geometry model that you've been building over the last few months, what that looks like, what some of the challenges are. Let's get into that.
Yeah. I don't think I'm the best person to talk about the geometry model, but that's why Alvaro is here.
Yeah.
But if we look at the tech stack of our organization, we really sort of have three verticals, right? We have a product team who are building a sort of software as a service set of tooling around like AI models for the advanced industries we talk about, aerospace, automotive. And largely that tech stack is your generic web service tech stack, right? It's your Kubernetes cluster, your Docker containers running APIs for people to interact with models or data stores. And then we have delivery who use our SaaS offering both internally and with their customers. And then we have our research group of people, which is where the geometry model comes from too. And if we look at the past few months at PhysicsX, we looked at running the training and data processing on something like Kubernetes, which, whilst a great tool, isn't necessarily the best fit for everything. And one of the things we wanted to do was really simplify with how our machine learning engineers may need to use cloud infrastructure, for example. So we didn't actually end up using Kubernetes for this. We ended up using some of the AWS native tooling, such as AWS Batch, and things like FSX for interfacing with S3 through POSIX compatibility, which really helped us speed up the development of the geometry model by reducing the complexity and the need for people whose jobs it isn't to be cloud engineering, but they do have a job to do as well. So we remove the need for them to learn new paradigms and new principles in what they're building. And largely we had two sets of training. So we had a sort of base training, or we had three sets of training. We had a base training run around May on a very small number of GPUs, where we started to implement multi-node parallel processing, which fed into our sort of two larger runs, which were across hundreds of GPUs, 128, I believe, sort of A100s in AWS over about 4 weeks. And then we did another run about 4 weeks straight after that. So if we look at our research team who were building the models, they were interfacing with building Docker containers to run on AWS Batch through some of the built-in multi-node parallel processing features across NVIDIA GPUs. And then Alvaro can probably tell you more about the geometry model itself.
So I think, first of all, in terms of what the model does, it's basically essentially a model that understands geometry. And what that means, it's a model that if you it is able to reconstruct any type of geometry. And so from airplanes to simple boxes to cylinders to more complex weird shapes and benches and things like that. And it's been basically trained on about 25 million meshes. So LLMs, they tend to be trained on the entire internet of text. We've done a similar thing, which is trained on the entire internet of objects that exist out there of geometries, and that accounts to about 25 million geometries. And a mesh is basically a technical word I've used to, which is just a type of file that represents an object, a geometry. And basically, this model is just an autoencoder that learns to represent an original geometry in a latent space, and then it learns to represent that latent space and convert that to that geometry. And that simple thing of just encode and then take a latent and then decode has a lot of downstream applications for engineering, for design, for optimization. And like I'm going to show an example later of the type of things that you can do with it.
What were some of those challenges working towards building that model? What was really difficult about that?
I can give a few examples of challenges more from the modeling bit. And then I'm sure, Jake, there's a lot of challenges from the cloud, from the infra and the compute bit. I think first of all, from the modeling bit, the first one is that we trained on 25 million geometries. Each of them is pretty big. So just getting that data and having that data available in the format that you need, that's a big challenge. Like making sure you have the data, making sure that the data is sensible, is useful. So that was one of the biggest parts of the project. And then I think overall it's just like thinking about the model itself, the architecture. I think this type of models, this type of objectives that we're trying to solve are pretty complex from a technical standpoint. Like finding the best architecture, the best parameters, making sure that if you're going to commit to train in a lot of GPUs for a very long time, making sure that you have the best model to do that before you train and before you spend a lot of money on that. Figuring out those parameters, figuring out how long you need to train for, how big your model must be. That's another of the big challenges that we face.
Got you. Jake, talk to us about the infra and compute challenges.
Yeah, I think these are, it's very similar to what Alfred was talking about. One of our challenges was the scale of what we were trying to do. We're talking about 25 million geometries, tens of terabytes of data. So even the data itself posed a challenge in being able to get that high throughput networking, low latency, so we could train efficiently. But similarly for PhysicsX as an organization, it was one of the first times we had gone for more than 100 GPUs at once. So really making sure that things like our CUDA drivers were set up correctly, EFA and AWS was set up correctly to get the benefits of what cloud providers talk about, fast internode networking speeds to ultimately train a model. We definitely learned a lot as an organization, and we'll take that forward in our next training round when we improve this model, when we build another model, for example. But largely, the scalability was our biggest challenge in terms of not having done it before. So it was a huge learning experience for us.
But yeah, we're going to talk about the tech demonstrator. I'm going to go back to you, Alvaro, in next couple of moments, which we can talk about some of the use cases for it. But I think especially with the phase of where PhysicsX is like taking some of those learnings and applying them moving forward. This is especially, GPUs at the moment, it's a relatively new ground over the last couple of years for people. If you can take some of those learnings forward and understand how you can engineer better, that's the kind of results that you're looking for, right? Alvaro, talk to us a little bit about the tech demonstrator.
The model that we trained, the large geometry model, was then fine-tuned on a much smaller dataset. So not 25 million meshes this time, a much smaller dataset of airplanes, but with an additional feature, which is not just a model that understands geometry and is able to generate airplanes and geometry, but also, most importantly, understand physics. So understand if a specific shape of a geometry is good or is bad. This model is not just a geometry model, but we fine-tuned this model to understand aerodynamics, to understand aircraft structures, to understand aircraft stability. These are the things that really matter for engineering companies. It's not the geometry, it's the geometry to meet a specific goal, which is a physics related goal. So for that, we built just a technology demonstrator as an example of the type of applications that you can use these foundational geometry models. And this is a demonstrator tool called Airplane, which is AI.airplane, pronounced airplane for simplicity, because AI.airplane sounds worse. And basically, this demonstrator is just a tool. It's targeted at engineers, at hobbyists, at students at engineering schools that basically want to accelerate the conceptual design of an airplane. In engineering companies, getting the first mock-up of a good airplane, it takes many months of work. This tool can do that in a matter of minutes, and that's kind of like that's the value that this tool brings, like helping engineers make early stage decisions very quickly based on physics predictions that the model does.
Yeah, I love that. That's something that Jake touched on, introducing PhysicsX, speeding up that initial stage of design is something that, as someone who comes from a background of being non-physics, I thought that's really interesting. If you can use AI to actually create a simulation in rapid time compared to what, some of the design timelines are at the moment, like, it's great to see this use case of AI. So that's what I've been buzzing about, trying to get you guys on. Let's talk a little bit about the classical software engineering, data science, and machine learning challenges in developing this reference app. There are a couple of points around accuracy, confidence in the results, especially if we're thinking about aeroplanes and flying stuff, if you like. I know there were particular points on the classical engineering fronts that we wanted to talk about.
Yeah, absolutely. So I can talk about a few of those challenges. I think you mentioned like accuracy and confidence in the result, which is something that I find this tool quite useful for. Is that if you just go to ChatGPT or Claude or any other LLM or video generator or whatever, it generates some text and it gives you what it thinks is the answer. You ask a specific question, it gives you a specific answer, but you don't really know how much you can trust that answer. You don't know if that answer is correct. If you're using it for things like write a piece of code, like help me write this Python script, it's very easy for you to validate that answer because you just copy that piece of code to your terminal, you run it, and you see if it does the job. So it's quite easy to validate the results. But when you're generating an airplane and saying that this airplane has a lift of 10, unless you manufacture it and fly it, you won't really know if that lift is 10. What the engineers do in real life is run a CFD simulation, right? A computational fluid dynamics simulation or a finite element simulation. And that takes hours or days, depending on the level of the simulation. So we know that that is an issue, and we know that there isn't a real user-friendly way of validating these results, which is why one thing we really paid a lot of attention is adding uncertainty quantification to our model and to the tool. So basically, if you go to the tool, you generate an airplane, it will tell you this is the lift, but by the way, this is the plus minus. This is the confidence that we have. So if you are about to design an airplane and you are between three options, that the three look good to you, the three look like good results, but one has a very high uncertainty where the other has a very small uncertainty, you would trust the latter. So I think that's kind of like the key thing in terms of like giving confidence in the result, knowing that people cannot just 3D print and fly.
I love that notion. Is that a common notion in physics design at the moment, or is it where we are with our stage of AI development that you can actually introduce the confidence in what you're building?
In tools targeted to more traditional engineering, that confidence is very important. So if you want to create a tool that is helpful for engineers doing their day-to-day job, this is essential. If you're doing a tool more for the general public and just look to show cool videos or cool stuff, then maybe that's not as important. But if you want a proper real life application, you need to show how accurate you really think you are and how confident you are.
Yeah. What challenges do you find when engineering something for accuracy and confidence? What challenges are there that you're met with?
The main one is just making sure, like, train the model with the required architecture, use the correct modeling technique that enables you to give you that confidence, to return you that measure of confidence. I think if you think of how an LLM works, which is regressive and generates the next token based on the previous one, that technique doesn't really allow you to give a confidence of the final answer. You can, but it's not really a measure of confidence. It's more tricky than that. So we picked a model architecture that supports that easily. So I think that's kind of like that's the main thing that we thought about.
Got you.
One of the, like, as Alvaro's been talking, one of the things I've been reflecting on is if we look at the makeup of the organization as well, like people's backgrounds, their degrees from university are all physics based. So for these people, like, the accuracy is something that they can talk about and understand to such an extent. Like, it very helpfully informs how we build these models or build these tools, like certainly with our customers across advanced industries, certainly with like generalizing some of the outcomes that these models can provide as well. And I think that's probably a really unique thing to PhysicsX is there's just over 100 of us. Most of us, not including me, have a degree in something that is physics-based or conventional engineering-based, which is really different to how we've seen it in other organizations as well.
I think that's actually a really good point and something I hadn't thought of. Obviously, I've looked at some of the founding team, incredibly smart people, but if all of the business has a culture of they come from physics education, that is probably the way that you're taught, how you think. It's probably bled into some of your culture on how you do things. So again, probably quite a unique opportunity for you, Jake, coming into the business with a different background, different way of thinking. Jake, you're probably thinking about some of these challenges over the next 12 months as the business grows. Are you thinking about some of the cloud computation challenges that might come with the sheer volume of scale of people using the platform, the evolution of just how many models you're developing, et cetera, et cetera? Are you thinking about those things already? And if so, what's on your radar?
Yeah, for sure. I think like the large geometry model we've been talking about is one of many that are ending up in a library, and these all require data to train on. They require people to support them day to day, and that is a scale challenge. Again, like we were talking about training that and scalability being a challenge there, but also helping people interface with this, not only from a software point of view, but also from a point of view that makes sense to them. As this starts to become more of a generic mainstream tool for people to use, if we look at Airplane, for example, there are people whose backgrounds won't be in physics, or they won't understand, and I certainly didn't when I started here, about lift and drag and cargo weight and all of these things that make up a good aeroplane design. And I think that's a really powerful thing, to be able to bring something like physics that requires quite a high understanding of mathematics, for example, to more people. And as someone who proudly doesn't actually have a degree, and I don't really want one anyway, as much as I'm sure they're useful, being able to work with a team who are incredibly smart and understand these things, and also are happy to help you learn about these things, is something super useful. I think as we grow as an organization, we will find that there are challenges that we haven't thought about, we don't know about. But that's what makes it exciting, right? Otherwise, what's the point? It would just be boring.
Yeah, 100%. No, I totally agree. The accessibility of physics for people, and what you're building, I think is awesome. We've touched on training and scalability a couple of times. It would be useful to get a little bit more into the detail of what makes good training practices and processes. What are the common pitfalls that you might find in training as well?
Absolutely. I think um, so first of all, in terms of the data set, like generating a good training data set for these models is actually quite difficult, because generating that data is very expensive, because our data sets are mainly data that we've run through simulations, and these simulations are like take days or even weeks to run, which means that you cannot just generate any geometry that you want and run a simulation. Like every item of data that you want to add to your data set must be the correct one. So knowing which data to simulate to add to your training data set is quite difficult, which is why if we now think about like the training, one of the main things that now I think most of our projects, most of our models that we're building with customers are starting to do more, is support active learning, which basically means that we start with a very low data regime, a model that has been trained on just a few simulations, not a lot, but the model itself then is being used to tell us what's the best data that we need to simulate to make that model even better. And that basically makes us, in theory, be able to generate the best data in the cheapest way, basically. So I think bringing active learning into the workflow is one of the things that, in my opinion, has been a big success over the last months at PhysicsX in different projects, and something that I highly recommend for situations, for tools, for models where generating data is actually quite expensive.
Got you. What are common pitfalls?
I don't have a strong answer for that. I'd say that sometimes actually like evaluating this type of models, this is not the standard machine learning where you have an F1 score, or a precision or things like that. So actually there isn't a single way of evaluating how good a model is at predicting the lift coefficient on 1,000 different airplanes. So the main pitfall, I'd say, it's picking the wrong evaluation metric or being too led by evaluation metrics that actually don't really are not as informative as they should, which end up sometimes making incorrect decisions due to that.
Okay, that's pretty good insight. That is pretty good insight. I've heard that a couple of times when we've interviewed a number of people. Being led by data that might not be correct is sometimes a common pitfall. Before we wrap up, you guys have been on a phenomenal journey. You're London and New York based. It would be great to hear about some plans maybe for the next 12 months of what you can share, whether that's products, releases, growth. But I want to give the mic back to you both to do a little bit of a road show on what you're going to be doing over the next 12 months.
I think more the question might be, where do we start? I mean, like we have, there's a lot of stuff coming up for PhysicsX, and I think one of the things I'm really passionate about, like personally, is the people to make that happen. So we're still growing as an organization. In 2024, we doubled in headcount just over, from 50 to just over 100. And as we go into 2025, we're still hiring people across both the London and New York office. And we're very, very lucky with the people who work here and the people who are going through our recruitment process, of that people who their bread and butter is physics, or their bread and butter is machine learning or software. And they have a very, very keen interest in the work we're doing. They see the benefits of it. I expect we're going to grow much, much more through 2025, similar to our sort of growth rate this year, to be able to support all of the things we're planning, whether that may be more geometry model training or more sort of web-based cloud engineering. Who's to say? Who can reveal it? Probably not me.
Yeah, and I think on top of that, echoing everything that Jake said, I think another of the things we are pushing more is actually exposing more of the work that we do to the world. So this is just a first example, this demonstrator, this airplane tool. But we want to go a step further. We want to publish more of the work that we do and present the world for more technical audiences, but also do more like live demonstrators of the technology that we're building. So I think what's next for us from a research, from an ML point of view, is also just being more show off to the world of the type of work that we're doing.
Love that. Some more active learning, some road showing, talking to people about what you're building, growing the business with smart people. I'm really interested to see more of PhysicsX. Like I've said throughout this podcast, you guys are on the mission to building something really incredible. I want to say a massive thanks for coming to join us. For people listening across London, New York, software engineering, product, machine learning, people from physics backgrounds, come and check these guys and girls out. They're doing some incredible stuff. They've got two smart people representing them here. So please do that. And of course, a thank you to you both for coming to join us. I really, really appreciate it.
Thank you so much. It's been a pleasure. And yeah, please, people listening, join us. We're a great company, great culture, great people, building great tech. So it's a great opportunity.
Good.
I think just to echo what Alvaro is saying as well, like you don't have to join us, you can just talk to us, right? I think over the past few months, being at AWS reInvent and other sort of conferences and roadshows has proven we love talking about what we do, which is a really great thing. And we're always interested in talking to more people about it too.
Yeah, good.
Exactly.
That's a really good point. You know, with your simulators, your demonstrators, talking to more people and spreading the word about PhysicsX. For people listening, careers site will be down below, but do go and check out PhysicsX and see more about what they're building. And of course, likes, shares, subscribership, all of that good stuff is great for us, keeps this little ecosystem buzzing around. So a big thanks both. Big thanks to PhysicsX, and from everyone at Engineers. Bye for now.
Thank you very much. It's been a pleasure.
See you later.
Hey guys, thanks for watching this episode. Massively appreciate you listening and checking in with us. If you want to find out more about us and what we're doing, please check us out on social media. What we're trying to do at Engineers is build a community to drive knowledge sharing and experiences. On Twitter, we can be found at Engineers.io. It's no_. We've also got a website, which is engineers.io. These links will all be posted in the description. Any feedback and comments are massively appreciated. We're always looking to improve on where we can. Thanks, guys.